I'm going to be offering Cal 3 in the spring. Now I know a lot of you don't need Cal 3. Some of you may. Some of you might not be sure if you need Cal 3, but right now we're going to offer only one section of it, and it's going to be offered on, right now it's on Monday, Wednesday from 1 to 2:40. Now this is somewhat flexible because I'm teaching it. I want the class to make, so if you're interested in taking this class and you know for a fact that this isn't going to work for you, just talk to me. These are my other classes, so just think about it, okay? Think about it. I know at least one person thinks that they need it or want to take it. Now, let me give you some personal advice, okay? How many of you have to take engineering analysis? I'm sorry, I'm getting over something. I was congested all weekend. And engineering analysis, if you're an engineering major, most likely you're going to have to take a class called Engineering Analysis 1 and 2. And that class is the weed out course for engineers. I mean, that's basically what it is. And I'm going to show you the table of contents for a textbook for engineering analysis. So it's just, I'm sorry you can't see this real good, but this is just, I just grabbed a random engineering analysis textbook, and the first section is differential equations, okay? The second section is power series. We're actually going to talk about power series in this class. Laplace transforms we don't do in here, but by the time you get here and you understand power series, you can do the transforms pretty easily. Matrices and determinants, that's linear algebra. You heard of that class before? That's linear algebra. Vector analysis is Cal 3, okay? And then you keep on going. This is, I doubt you get to this in the first class, maybe in the second, I don't know. So what I'm trying to say to you is that if you just look at these chapters in the book, the first chapter is differential equations. You're not going to get a full semester treatment of differential equations in this class. They're going to expect that you have some background with it, and they're going to show you how to solve differential equations real fast, and then you're going to get into applications. Application, application, application. So the thing that students struggle with in this class is that the math is not the main idea. The application is the main idea. So students struggle trying to learn the math while they're simultaneously trying to apply it to problems. Does that make sense to you? So my recommendation is if you have the time, have the resources, I recommend you take differential equations and Cal 3 and linear algebra before you take this class. Now I know that's like, oh my God, that's a lot of, it is, but if you get those classes out of the way first, then this course becomes a lot easier to do because the math you've already got the foundation for. So, like I said, vector analysis is basically Cal 3. So in Cal 3, what we do is we do all the stuff we did in Cal 1, all the stuff we do in Cal 2, but we do it in higher dimensional space. So you go to 3-dimensional space, 4-dimensional space, and as soon as you step off the flat sheet of paper, you have to start using vectors. So that's why we call it vector calculus or vector analysis, all right? So I'm not trying to sell you on it. I mean, well, I kind of am, but it doesn't matter. If the class doesn't make, I'll teach another class, but I really would like for it to make. I think your success in that engineering analysis class is, I guess you have a higher chance of doing well if you get some of this math out of the way. Question?
Will you be the only one teaching it, or will you be more classes?
It's the only one we're going to offer. Yeah. The reason is because we have to have the class make, right? So we don't have a lot of people that need it. We have the same problem with differential equations. We have the same problem with linear algebra. Like normally we only offer those once a year because they don't always make. So, yeah.
So you said the classes you recommended was differential equations, Cal 3, and linear algebra?
And linear algebra. Yeah, and all of those courses can be taken concurrently. Now, I don't recommend that, but you could take 2 of those at the same time because you don't have any. The last prerequisite you have is the Cal 2.
Would one of these be available during the summer?
Linear, no. Differential, no. Cal 3, maybe. Maybe. But again, we stopped offering it in the summer because we weren't getting enough students. Although I will say, I get It's made in the summer in the past because we had a lot of students come in from out of town, right? They're off at UT or wherever. They come in, they want to knock a class out in the summer, right? So it'll take something like that.
Make it in the spring, is it more likely to be offered in the summer?
I don't know if it'll get offered in the summer. We haven't made that schedule yet. We'll make the schedule for summer before we'll know if this class makes. So we won't even, we'll probably put it there, but whether or not it makes is a different question, or is different. Okay, yeah. So Cal 3 I think is a fun class because it's three-dimensional. Even if you're like, I don't know, anything that you think you're going to be working in three-dimensional space with physical things, that's what Cal 3 is about. All right, let's get down to business. So today we are going to we're on schedule, okay? We finished partial fractions last week, and we're going to start today. I have all these sections together. Basically what we're going to do is we're going to figure out what the definite integral is. All right, we're going to spend a lot of time on the theory behind it today, and at the very end we're going to take away one simple thing. Right, so a lot of today is just so that you understand geometrically what is going on, all right? And that your understanding today will help you tremendously when we get to chapter 7, all right? So I really need to set today up so we're looking down the road to get to chapter 7 and you understand how to do this. So focus today on understanding what I'm doing, not so much like, I'm going to have to do a problem like this, just understanding what I'm doing. And then next class we'll get into 6.6, improper integrals. This section has two parts to it, so we'll do 6.6 part 1 on Wednesday, and then next Monday we'll do the second part, and then we'll have next Wednesday our exam 2. It's going to be a monster exam, yes? It's going to have a lot of stuff on it. In terms of the 6.6, I'll probably put stuff from Wednesday this week on this exam, just minimal. Nothing from next Monday will be on the exam. So when we get out of class this Wednesday, that's it. Whatever we finish Wednesday, that's all fair game for the exam. I'll give you some sort of review or guide. I will for this test. But look what it's going to cover. I mean, integration by parts, right? Because on this test, we had a real basic one, I think. Here, we have more trig integrals, trig sub, right? Partial fractions. So this is going to be that test where you sit down and you look at an integral and you're going to need to know what to do with it rather than spending 20 minutes trying to figure out, well, what do I do? What do I do? So this is going to be, it's a challenging test for a lot of students, right? All right, so that's the plan. Any questions? No? All right, we have to get some preliminary things out of the way here before we begin. I mean, it's part of today, but we need to take care of some prelim stuff, and then we'll get into what the definite integral is. Right now, though, here's where we are. We know that what this notation means, right? This notation means, hey, go find the antiderivative of this function, right? Treating x like the independent variable. When we do it, we get some answer. And that answer, capital F of x, is some family of functions because of the plus c, right? So that's the indefinite integral. Our goal today is to understand what the definite integral is. So first, we set up some prelim stuff. So some preliminary stuff. All right, sigma notation. All right, so we all need to be somewhat comfortable with sigma notation. This is going to come up again in chapter 8, sequences and series. So sigma notation is basically a notation we use to be able to write something that would be very long and cumbersome into something nice and tight and compact. So let's say I wanted to take some expression, let's say a sub 1 plus a sub 2 plus a sub 3. And I had, let's say there was 103 things that I wanted to add together. The first thing I'm adding, I'm calling a sub 1. I don't know what it is. It could be a number, could be a function. It doesn't matter what it is. It's just something I want to add to something else, add to something else, add to something else. And I want to stop. I have 103 of these things to add up. What I can do to rewrite that in a more condensed notation is to say that that's equal to the capital Greek letter S, sigma, right? Sigma stands for sum. And then what I do is I start on the bottom by writing k equals 1. And then on the top, I'm going to write 103. So what this is, that we call this number down here, this is your starting, oh, dead. That's your starting index. Okay, so this is your starting index. The letter K is arbitrary. It could be any letter you want. Now, normally we use K, we use N, we use M. I've seen, just things we stay away from are things like X, Y, Z. Those are normally reserved for the variable within a function. But here, K is 1. That's your starting index. And then here, this number up here is your stop. Okay, index. And that means what I'm going to do is I'm going to start adding things up, right? Sigma means I'm going to add things up. I'm going to start with K being 1, and I'm going to start cycling through the integers. 1, 2, 3, 4, 5, 6, and I'm going to stop when I get to 103. Now, what is it that I'm actually adding up? All these, right? So the thing that changes on all of these is this subscript 1, 2, 3, right? That subscript changes. So what I need this expression in here to be is A subscript K. Do you all see how this works? Say, start with 1, replace that K with 1, and you would get A sub 1, right? A subscript 1. There. Plus, now you let K go up by 1. Now K is 2, A sub 2. Boom. Plus, now you let K go to 3, A sub 3. Plus, and you keep going until you stop at 103. Make sense? How many of y'all have seen this before? Should have seen something like this in college algebra, maybe? All right, here's a specific example. Here's a very famous one. Let's say I wanted to add up, let's see, K equals 1. Let me stop at 10. Let me just do K. See, over here, I just gave you some arbitrary expression. I didn't tell you what this was, right? You could look at this as being some function of K, whatever it is. Here, I'm actually telling you that the thing I want you to add up is K itself. So I start with K being 1, right? So this is equal to 1 plus, now I let K be 2, right? So this is just adding up 1 plus 2 plus 3 all the way until I get to what? 10. And then I'm stopping. Could we add that up? Sure, right? We could do 1 plus, and we get a calculator out real quick and do that, couldn't we? We don't need to, but I'm saying we could, right? Do you understand? Yes?
Sorry, if K equals, say 5, we go by increments of 5?
No, if K was 5 here, then you would start at 5. So if I did this, with sigma notation, you always increase by 1 every single time. All right, so this would be 5 plus 6 plus 7 plus 8 plus 9 plus 10. Now, you bring up a good point. What if you wanted to go up by 5 each time? Right? How could I change it so I could go up by 5 each time? Anyone know? So what if I wanted to add 5 plus 10 plus 15 plus 20 and do that 10 times? What would I put in here? 5K. You see? If I put 5K here, then when I plug in 1, what do I get? 5. When I plug in 2, 5 times 2, 10. Understand? 15. Now I'd have 10 of these. What would be the last one? 50, right? And we could figure out what that is. I'm not going to, but we could. So this, in sigma notation, I'm sorry, just it's hard for me to talk today. In the sigma notation, the K starts wherever you want it to start, usually at 1. But when we get to chapter 8, we're going to see that it's going to start at 0 sometimes also. So, but normally it's 1 or 0, and it always goes up by 1 each time. All right? And if you want it to go up by more, you want something else to happen, you adjust the formula that's in here. Okay? I'll give you one more example. How about this one? Another famous one. We'll go to 10 again. How about K squared? That's 1 squared plus 2 squared plus 3 squared plus 4 squared, right? 1 squared plus 2 squared plus 3 squared plus, and I go and stop at 10 squared. All right, so that's just the notation, right? That's what sigma notation is. You can put any formula you want. Any formula you want in here, okay? Anything. Doesn't matter what it is. All right? Doesn't matter what it is. Let's do one more. This one's a little tricky. One more. What about sum k equals 1? Let's go to 10. What if I just put 3 here? What do you think that is? Go ahead.
Wouldn't it be just the addition of 3 10 times?
It would be 3 10 times added together, exactly. So look, you let k be 1, right? If k is 1, what do you get? 3. Plus, now you let k be 2. You still get 3. Now you let k be 3. It's still 3, right? Every single time it's 3, and you're going to add all these up, and you're going to have a last final 3. And how many of these do you have? You have 10 of them, right? Right? So your answer here, what would your answer be? 30, right? Wouldn't it just be this number times that? Yeah. All right, I'm going to give you some nice little formulas here in a minute that we're going to use. But this is just to make sure you understand the notation. Any questions? All right, what about this? What would this be? I'm using this k again, all right? Just this formula, but what's the difference between that, and this?
Got a variable instead of
Yeah, so where am I stopping? When I get to n, right? I'm stopping when I get to n, but I haven't told you what n is. So this means I'm going to start with k being 1, so I get 1 plus, right? Now k is 2, 2 plus. Now k is 3 plus, and I'm going to keep doing that until I get to the very end. The last one would be n. That's the sum of the first n integers, right? That's the sum of the first n integers. That's what you could say that formula is, right? The sum of the first n integers. The sum of the first n integers. Assuming that we're starting at 1, right? Well, there is an actual nice answer to this, right? And I'm going to give you this answer. I'm not going to prove it to you. I'm going to tell you what this is, all right? We have 2 ways of proving this. I can prove this with a kind of a geometric proof, and then there's another way I can prove it using what's called the principle of mathematical induction, which is a super awesome thing. If I have time for it later, I'll show it to you. But for today, you're just going to take it on faith that this actually just adds up to be n times n plus 1 divided by 2. I didn't tell you all that story about the kid, right? I know my Cal 1 I probably did. Do you remember the story about the kid who added up the numbers in class? No? Did I tell you all that story? I didn't tell you all that story? Okay, I'm going to have to come back and do it some other time. All right, so look, this is actually, you might wonder why this is true. I want you to just take it on faith, all right? For right now, take it on faith that that's true. So check this out. Look at what this formula says. It says if you want to add up the first n integers, that is just equal to this. So come back over here. If we want to add up the first 10 integers, according to that formula, what would it be?
10 times 10 plus 1.
It'd be 10 times 10 plus 1 divided by 2, according to this, right? All you do is take the last number, right? That's the nth number right there. Plug it into that formula. Let's do that real quick. What is this? 55? 55. So if you got your calculator and did it, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, I bet you get 55. Okay? That's not a coincidence. That is true for any n. So if you add up the first 100 numbers, you would put 100 times 101, divide by 2, and that would be your answer, right? We need that today, all right? That's a very nice formula. So put a little star next to this. The next one we need to know is this one. Sum k equals 1 to n of k squared. So what is this? Well, it's this one over here, isn't it? 1 squared plus 2 squared plus 3 squared plus 4 squared, right? So on and so forth. So this is 1 squared plus 2 squared plus 3 squared plus all the way out to n squared. So you could say this is the sum of the squares of the first n integers, right? It's the sum of the squares of the first n integers. And this has an answer as well. Without me proving it to you, I'm going to tell you what it is. You ready? It's n times n plus 1 times 2n minus 1 over 6. Hold on. I know it's 6 on the bottom. Plus 1, that's what I thought. Okay. It's plus 1 in there. 2n plus 1. There we go. That's our formula. So according to that formula, I'm going to need you to get your calculator out. What would the answer to this one be right here? This one would be, what's n for us here? 10. So we would go 10 times 10 plus 1 times 2 times 10 plus 1. All of this divided by 6. This better be a nice whole number, right? If it's a fraction, something's wrong. What do you get? 385? Everyone get that? Yes? Okay, so 385. I wish we had enough time for me to go through the proofs of these using induction. Induction is such an awesome thing in mathematics. It's like, how do you prove that this is true, right? You can show it's true for, like, you could check it, right? We could check it, but how many times would you have to check it to show it's true? You have to check every single possible number, which is impossible for you to do, right? You would run out of time. So how do we prove things like that in mathematics? We use this thing called PMI, Principle of Mathematical Induction.
So for like that exact one, 5, 8, what formula would you use?
Good question. Can I come back to it? Let me give you one more formula. Last one. Pardon? No, but remember I said today is going to be about you understanding something. Don't worry so much about, oh, I'm going to have to do this. When we finish today, you're going to be like, oh, okay, well, what I need to take away from this, I can do. This is just all the setup for what I'm about to do, all right? They're in your notes, though. These are in your notes. The formulas, if you look, I have a formula. In our notes, there's a formula, or there's a, the notes are called Chapter R, Riemann sums, and these are the common formulas. They're in here. So just look in your notes. They're there.
We can add these to our formula sheets too, right?
What's that?
We can add these to our formula sheets?
No. You won't need them.
Okay.
You won't need them, yeah. So yeah, don't add anything to your formula sheets unless I say, because that could get dangerous during a test if you have stuff written there and you're not supposed to have it. And even if it doesn't help you, it's still not fair to let you write on your formula sheet and everyone else doesn't. You know what I mean? All right, the last one is k cubed. This would be the sum of the first, the sum of the cubes of the integers, right? So this would be 1 cubed plus 2 cubed plus 3 cubed plus all the way until you get out to n cubed. Now, I didn't give you an example of that over here, did I? I didn't. But I'll tell you what the answer is to this. It's actually kind of a very weird answer, like you wouldn't expect this. It's n times n plus 1 over 2. Does that look familiar? It's that answer, right? Squared. That's weird, but that's what it is, okay? That's what it is. So let's check this one. Let's see if this formula is right. Let's do an example. If I do sum k equals 1 to, let's just go to 5 of k cubed that would be 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. I need someone to do that on your calculator. And then I need everyone else to do this on the calculator, replacing n with 5. So if I use that, I'm going to get 5 times 5 plus 1 over 2, but that's squared. What is that? 225?
Yes.
225. Y'all get 225, adding them all up?
Yes.
The formula gets that, okay? The formula gets that as well. So, but again, just because it did it once shouldn't convince you that it should always work, right? But I'm telling you it does, all right? So these are just 3 really nice formulas that turn out to help us with what I'm going to do today, all right? Any questions? Yes?
Do you know the names of this? Like what's
There's really no names. It's just the sum of the first n integers, the sum of the squares of the first n integers, the sum of the cubes of the first n integers. And imagine that I could keep going, right? 4th power, 5th power, 6th, and there's formulas for those as well. Now, I want to address that question about the 5, right? The 5k. How would we do this using that formula? Well, there's another property. I was about to give you properties of these things. One of the properties of summations like this is that if you have a constant in the summation, right, a constant can come out and be multiplied and then just have k here. You see that? Now that's a property. I need to put it down on the board, but think about why this is true. Don't all of these have 5s in them? Right? These all have 5. So you can factor a 5 out, and then it'd be 1 plus 2 plus 3 forever, right? I mean, sorry, forever. I'm already in chapter 8, sorry. Until I get to what, 10? Right? That's what this is, right? And this sum is what that notation means. You see it? So constants can be factored out. So let me put some properties of summations. Now I'm only going to give you 3 properties. There's a lot of different properties for summations, but here are the ones that we're going to need for today. So the first property is I'll just put that property there. If I have a sum, k equals 1 to n, of some constant times a sub k. So I've got a constant in front of some formula that has k in it. Then the constant can come out of the summation, and then I just have whatever the summation is, like that. So constants come out. That's your first property of summations. Now, I need to be clear on something. All of the properties I'm giving you right now are for finite sums, meaning this n is not infinity. In chapter 8, this n is going to be infinity. So this is only for finite sums that these properties are true, especially this next one. So I should put up here, finite sums only. A little disclaimer, okay? If I take the sum, k equals 1 to n, and I have in there a sub k plus or minus b sub k, that you can split this into 2 sums, the first a sub k and then the second one, the b sub k. Let me give you an example of that one over here. So an example of this would be if I did sum k equals 1 to 20 of 3k squared minus 4k. This property says that as long as it's a finite sum, if I've got 2 things being added or subtracted, I can split it into 2 sums with addition and subtraction. So I could rewrite this as sum k equals 1 to 20 of 3k squared minus sum k equals 1 to 20 of 4k. Understand how that formula worked, or how that property worked? What else could I do?
You could pull the constant.
I could pull the constants out, couldn't I? So I could pull this out, 3 times sum k equals 1 to 20 of k squared minus the 4 could come out, sum k equals 1 to 20 of k, right? That's the first property. With me? What else could I do? There's one more thing I could do. And this is a big deal here. Didn't I tell you that there's a formula for this? And didn't I tell you there's a formula for this? I gave you the formula, and I told you I can't prove it, or I'm not going to prove it. But didn't I tell you what the sum of the first squares of the integers are up to n? I did, didn't I? Gave you a formula for it. Now here we're not going to n, we're going to 20, right? So you could say that that's equal to 3 times, what was the formula for k squared? It was n times n plus 1 times 2n plus 1 over 6, right?
Yes.
For the squared one? But for us, n is what? 20, yes? So I could write 3 out front times 20 plus 1 times 2 times 20 plus 1, all of that over 6. Do you all see that the summation's now gone? Because I've used the formula for this. And then minus 4 times, what's the formula for just k? N times n plus 1 over 2. And here for us, n is 20. So this could be 20 times 20 plus 1 over 2. And that I could just calculate, couldn't I? I could figure out what this number is. But the main thing is to understand we're using the properties to get to this point, right? Okay, last property. And then we're going to get down to business. The last property we actually looked at earlier. If you have sum k equals 1 to n of some constant c, this is just c plus c plus c plus c plus c plus c n times. That's what that is, right? So this is just c times n, right? That's all that is. It's just this number times that number. We did that example with sum k equals 1 to 10 of the number 3, right? And the answer was 30. That's what that property is. Okay, we ready?
Sure.
All right. This is all just, we need these tools in our toolbox to now attack the main question here, all right? Those are also in the notes, okay? So the fundamental